Hi students, welcome back to the online video lectures on DSP. This is the 8th module on Discrete Fourier series and Discrete Fourier Transform. And in this module, we would be discussing in detail about performing linear convolution using the Discrete Fourier Transform. Okay, I'll move on to the desktop sharing mode as well as the notebook. Okay. uh, yeah, so let me first start with discussing about what could be the motivation for doing a linear convolution using the DFT. Okay, let's start with that. Okay. um, well, before that, let me write some basic things about the DTFT. Where do we get the linear convolution, and what about the DFT part? Okay, so let's say I have a series x1 of n finite length sequence, okay, whose DTFT is x of e power j omega. Okay, since it is x1, let me call it as x subscript 1. Similarly, let there be another sequence with which I would like to convolve the above one, x2 of n. Let's call the DTFT of it, okay, discrete time Fourier transform of it, as x2 of e power j omega. Suppose now in the time domain, if I am performing a linear convolution, x1 of n linearly convolved with x2 of n, what would be the DTFT of it? Okay, that would be multiplication here in the frequency domain, x1 of e power j omega into x2 of e power j omega. For some reason, assume that I would like to consider that I would like to perform in the frequency domain a multiplication instead of doing a convolution in the time domain, and then compute the inverse transform for it to get the time domain. So first let's think that's absolutely, in this case, would give you x1 of n linearly convolved with x2 of n. Is there any problem in doing this in frequency domain and coming back? Yes, of course there is a problem. The problem being these are continuous variables, and there is no way you could vary it continuously and then find inverse DTFT of it, right? So that's exactly the reason why we would be moving on to discrete Fourier transform, where the same sequence x1 of n, let's assume the DFS of it is, let's say an endpoint DFS of it is x1 of k. Then let me also, sorry, it's not DFS, I would like to compute DFT. Yeah, of course, the reason being this is a finite length aperiodic sequence. Okay, now let the DFT of x2 of n be x2 of k. Now anyway, now I am going to this x1 of k and x2 of k, we already know are in fact samples, uniform it's like x1 of e power j omega uniformly sampled at a distance of 2 pi by capital N, n being the length of the endpoint DFT, right? So that would, these are in fact the samples of x1 of e power j omega and x2 of e power j omega. Now if I now multiply these samples of length n here, each of them is, okay, or it could be whatever the length of x1 of n and x2 of n, endpoint DFT I am computing here, okay, endpoint DFT. So they are having a length of capital, so the n samples is what I have taken and multiplied the respective samples, and for that if I take DFT, what do I get here? I would get this, already we worked out in our earlier modules. This would give me the endpoint circular convolution of x1 of n and x2 of n. Now so we have seen again, and if you have done the examples in the previous module, you would note, yeah, what you are getting here is a endpoint circular convolution, correct? Endpoint circular convolution. But what you are interested, circular convolution, okay, but what you are interested is linear convolution. The question now would be, can I somehow get from n-point circular convolution the result of linear convolution? We have not done it mathematically, but what we have seen in the couple of examples that have been given as exercises in the previous module is that for certain values of n, okay, that we have already seen. So for certain, okay, this what exactly is this certain, we will come back. For certain values of n, we noticed that the linear convolution, which is x1 of n convolved with x2 of n, is in fact equivalent to the n-point circular convolution of x1 of n with x2 of n. Okay, so if we are able to figure out the appropriate value of n, then this would simply, the circular convolution would, all I need to do is take some samples of DFT of x1 of n. At the same rate, you take the same samples of x2 of n in the frequency domain, you multiply the respective ones and take inverse DFT of it. Okay, and that would give you the circular convolution result, which would be exactly same as the linear convolution. Okay, why would I like to do it in this way? Why should I do it this way? Okay, that's why should I do it in this way. That's a very valid and genuine question, right? So that's what we would try to get some intuition about this. Okay, so for that, what I will do is, again, this is not, I'm not keen on giving here a mathematically robust numbers and computational complexities here, but I will be happy to just give you an intuition and to give you some appreciation or intuition that this is indeed would help you. Okay, so suppose I want to perform linear convolution of two sequences, x1 of n and x2 of n. Okay, so assume that the lengths of these sequences are, let's say, L and n. Okay, this length of this x1 is n. Okay, and for the sake of simplicity, let me also consider that L is approximately, okay, n I would use for n point DFT. So let me replace this variable with p. Okay, let me also assume that this again, later you would realize that this need not be the case at all, but this makes my life simple to give you some quick appreciation and some numbers about it. Okay, so this is what I assume. Now what I would like to first see is what would be the computational complexity if I am doing this linear convolution in the time domain. So how do I do the linear convolution? Well, this would be equivalent to k varying from minus infinity to plus infinity, x1 of k into x2 of n minus k. Correct? That would give me the value at n. Okay, in the output at n. Right? Do I have to do this infinite values? Not really. Let me also assume that both these this is assumption 1. Okay, assumption 2 would be, okay, both sequences start from n equal to 0. Okay, this is also is not at all a problem. I could, once I know the length, this is just, I want to keep some numbers here, so that's why I'm doing it this way. So I would then keep it k equal to 0. Okay, and I would keep here the length, assume that that length is L, so I would put L minus 1 here. Okay, and what would be the what would be the length? Okay, this again we have worked out earlier while talking about the linear convolution. We have discussed it there that the maximum length of x1 of n linearly convolved with x2 of n would be, if I give you as L and P, L plus P minus 1. This we already discussed it. If you don't know that, or if you don't remember that, I'll anyway come back to that after some time. But for the time being, even if you do not know it, if this is of length L and that is of the P, the maximum non-zero length that could be there is L plus P minus 1. Okay, I'll come back to that. So how many computations are required here? If I, so this, in fact, the summation has to be computed now. So summation has to be computed at summation has to be computed for n varying from 0 to L plus let me not summation to be computed for L plus P minus 1 L plus P minus 1 values of n. Okay, it doesn't really matter where n starts or ends, that's the case. Now for each n, if you look at it, for each n, how many calculations are required? I need to do this L, so there are L multiplications I have to do, L multiplications, and how many summations? Of course L minus 1 summations. Okay, these are what I have to do, and there are L plus P minus 1. So the order of computations, okay, let me put together this, let's not worry about minus 1, L being large. So order of computations here is L for each n. So total order of computation, such I have to do L plus P minus 1. Total order of computations would be order of L plus P minus 1 into L. Okay, now that I'm sure you might have studied in some other courses, how do you compute the computational complexity? These two of the same length, similar values, let me simply consider L. So you take, just simply keep track of the highest order there. So this would be of order of L square if you are directly going to compute the linear convolution. Okay, now suppose instead of that, what is that I could do is, as we mentioned here, what's the procedure that we would like to follow here? Let me first give you the procedure and then come back to the computational complexity of it. Okay, so what I would like to do is here, let's say as a first step, I want to compute n point. Okay, so far we are not looking at, and we don't have a, we are not bothering at this point of time what's the value of n that would give us. Okay, n point DFTs for these x1 and x2. So let's call the n point DFT. So we would compute x1 of k comma x2 of k. That's what we would like to do, right? Then as a second step, what you could do is, then you compute x3 of k, which is simply a multiplication of x1 of k with x2 of k. And as a third step, I'd like to compute some x3 of n, which is inverse DFT. Okay, IDFT I'm using it, otherwise like you could keep DFT inverse symbol there, of x3 of k. Okay, that's how I would do that. And this x3 of n, what would be that? In fact, would be this, you know it from what you have written here, same as that. So that's essentially is equivalent, is exactly equivalent to x1 of n, so n point circular convolution of it with x2 of n. And we, under certain conditions, for a given value of n, it is possible, which we again will come back to that, to be equivalent to x1 of n linearly convolved with x2 of n. Okay, let's now analyze the computational complexity of this procedure. Okay, now the advantage comes from the fact that there are certain set of algorithms that would give you the DFTs and inverse DFTs very efficiently. Even if you have, of course, even very basic algorithms for computing the FFTs or inverse, that's what you call as fast Fourier transforms. They will be, for example, their order will be, assume that it has a length of L, okay, or this L equal to n, for example, you call it, okay, let me call n point DFT is what I am computing it. So then its order will be order of log n to the base 2. These are very, I'm talking about very basic algorithms which we would be discussing in the upcoming classes. They have a computation complexity of order of log n to the base 2. And now what about this? That's for step 1. Okay, that's the computational complexity for step 1, as well as step 3 is also what you are going to compute their inverse DTFT. So that's step 3 for those steps. And then what about the step 2? Step 2, x3 of, for the step 2, what would happen for step 2? For the step 2, you have to find out a multiplication of x1 of k and x2 of k and then sum them up. Okay, so it's just doing for one way, as if you are doing for n value, you could figure it out that this is of order of n computational complexity. That implies the overall computational complexity here, here you just retain the maximum one as this computational complexity, order of n log n to the base 2. Okay, again, if you are not earlier familiar with computing these computational complexities, don't worry about the minor details here. We'll come back to that while we are dealing with FFT, and we will do it in bit more detail. Okay, all I would like you to, it is enough if you understand anyway, assume that this L is similar to n. Okay, then look at here, the first conventional straightforward approach. You see here, as I am varying n, okay, order of, how does the order of n square would change for increasing values of n and for higher n values of n versus n log n to the base 2, you would see that computational complexity here would be less, and of course that's why you would be going for these methods. Okay, so hope that is clear for you. So that's the motivation, and that's the procedure as well as included in the motivation itself. The computational provided you have efficient methods for computing the DFTs and inverse DFTs, then obviously if you find out if you multiply the DFTs, take inverse DFT and do something else on top of it, then you would get the more efficient way of computing the linear convolution. Okay, hope those points are clear to you. With that, let me now go into a more thorough discussion on the length of this sequence. Okay, and also along with that, what would be like, when would we get, there are two more other things that I am going to discuss now in this video lecture. Okay, the first point is what would be the maximum length of convolution. I have already told it as L plus P minus 1, but I would give you why is it so in bit more detail, and after that you would be discussing when is it that circular convolution is equivalent to the linear convolution. These are the two things that we would be discussing in the remaining part of this video. Okay, for this, yeah, as I mentioned, you have two sequences. You compute, this is the same procedure I have written there. You compute the DFT, you take the inverse DFT, and that in fact is equivalent to circular convolution, but that's also would be equivalent to n-point linear convolution. Now what I would like to show you here is what would be the maximum length when you are having two sequences. Assume that one is x1 of m and x2 of m. I would like to do a linear convolution of them. So what would I do? Assume that it's x2 of m I am flipping, okay, and wherever at whichever value of n I would like to compute, that's by that value I would shift it, multiply the corresponding elements of x1 of m and the flipped and shifted versions of x2 of m and sum them up. That's what I would repeat. So what we would like to analyze here is what would be the maximum possible length of this sequence. Okay, and again here without loss of generality, let me consider that both sequences would start at 0. Even if they doesn't start at 0, doesn't matter, except that these indices would change. Okay, other than that there won't be any problem. Okay, so the third sequence here is the one which is showing the flipped version, and you can notice here that this convolution would be non-zero only when there is an overlap between this and this. Okay, this of course, to calculate it at different points, what you would be in fact doing is you would be shifting this, in fact. Okay, that's what you would be doing there. So when do you have, so there should be an overlap essentially between these two sequences when you are moving it. Okay, this is something. Okay, this is flipped one, you could move it in either ways. For example, I want it at -1, I want to do it, for example, both are starting at 0. Okay, this is, you assume that, later you yourself analyze and you would realize that it's not a you are not losing any generality with this assumption. Okay, suppose if I want, you think of this as a trine with bogies, each one is a bogie, this is another trine. Okay, you consider this is a static trine and this is a moving trine. So basically you have some value when there is an overlap between the bogies, at least one bogie of that and this bogie or whatever engine, there should be an overlap there. Okay, so the moment it is there at x minus m, we'd have an overlap, but anything here, okay, in this region will not have an overlap, right? So what can you say there? Then only it would start from this length of the, so when there is no overlap, the summation would be 0, right? So x3 of n is 0 there, so it could start from 0 only. Here non-zero length would start from 0. Okay, then we have to see on the other end what could be the maximum value, and other assumption is this is of length L. Okay, this is of length P, and now you could see here there could be as one so this is, so if even just one bogie, I'm calling one index as bogie, maybe that's, for me I find it easier to visualize here, if there is even at least one overlap here. Okay, so that means what I could say is this length here for this is L, this length is P, so I could go to the other extreme. To what extreme could I go there? For example, as long as I have a sequence here, this, let me call this as 1 2 3 so on, so even this was fine. Okay, then this is like placing, where is it that equivalent to placing? You would see there that you could in fact go till this so unless this L plus P minus 1 length is what you would get, anything, so -1 m is keeping that at -1. Okay, and you could have values till L plus P minus 2 if you see it. So basically this is of length L. Okay, this is of length P. Okay, then the maximum where you could have an overlap is at least one should be overlap is there. So L plus P minus 1, this length is L, but you start from 0, so that means in terms of indices, this non-zero length indices would be 0 to L plus P minus 2. That's all. So hope this slide makes the visualization for you clear, that you have 0 values from x3 equal to -1 and anything further, and on the right hand side L plus P minus 1 equal to 0, and any n value above this also would be 0. So you could have a maximum length of 0 to L plus P minus 2, that means L plus P minus 1. Okay, that's to justify you that the length of this maximum length is L plus P minus 1. Okay, the whole analysis is based on that. Okay, so hope that point is clear. Now let me come back now to figuring out when will be the circular convolution. So the question that we are going to now take a look at is, when is circular convolution equivalent to linear convolution. Okay, that's what we are going to take a look at now. So for that, let's again write the notations, rewrite the notations here for our convenience. Let for x1 of n, the DTFT be x1 of e power j omega. Similarly, for x2 of n, let the DTFT be x2 of e power j omega. Right? Now, if I had a sequence x of n obtained as a result of convolving x1 of n with x2 of n, and that DTFT of that would be equivalent to x1 of e power j omega multiplication in the frequency domain, x2 of e power j omega. Now, I am considering a discrete time sequence in the Fourier domain that has samples. So this is what I would call it as x of e power j omega. Okay, since I am calling it as x of n, that's what I call it as x of e power j omega. And I am going to take samples of it, okay, at an intervals of 2 pi by n. That's what my x of k is. This is what I would do for 0 less than, k less than or equal to n minus 1. Okay, otherwise I would consider the rest anyway. This is 0. Notice here I am taking capital N samples of this frequency spectrum. Right? Now, this is something we have discussed in the last but one lecture. If you go there, if you take samples of a sequence, and to this, if you consider inverse DFT, if you don't remember that, please go back to the video lectures there. Inverse DFT, okay, and that whatever is giving you is you again take one sample of it, but from that you get an x tilde of n. Okay, this again periodic, you go back there. So this is periodic in nature. So what you want to create a periodic sequence from, you could think of it in two ways. You get x of n, okay, and from that you create a periodic sequence that I don't want to call it as x of n, let me call it as one period of that signal, okay, because there is this another x of n is there. So how is this xp of n is related to x of n? Okay, this is what we have done, the sampling of DTFT. So please go to that video lecture if you don't remember this, and we have seen there that this is equivalent to convolving x of n, right, with an impulse train, and that impulse train having copies at distances of integer multiples of n. So that's equivalent to minus infinity to plus infinity x of n minus r times n. Okay, now you take one period of this sequence, and that would give you the D inverse DFT in fact. Okay, this what you get is a periodic sequence. Once you take there, just get what you get, and then you take one period of it, that would give you x tilde of n, and that's equivalent to n minus. See, I'm not directly writing x of n here for a reason. If you again go back to the time domain aliasing, only when the number of samples you have taken are if this are more than or at least equal to the length of this, okay, number of samples you have, that time only this xp of n and x of n would be equal. Otherwise you get a periodic signal, but if you take one in one period, there is a summation coming from here. Okay, that's the reason why we are writing it first the periodic sequence followed by one period of that signal. Okay, 0 otherwise. So this question now boils down to when is xp of n is equivalent to x of n. Okay, this is what we have done in the second lecture back from now. Okay, so that we have figured out that if your number of samples you are taking, okay, if the number of samples you are taking are greater than or equal to, if you call these lengths of them as length is, if the length here is L, this length is what is it that we were calling it? I think if I am not wrong, we are calling it as P. Okay, then as long as this is L plus P minus 1, okay, because that's what the maximum length that X the convolution can take, you will have this. This is whenever n is greater than or equal to L plus P minus 1, which is nothing but the length of X of n. That's all. This is all we do. So how do we achieve now linear convolution through circular convolution? Is that you make the lengths to be equal to, you make the lengths of each sequence, you take n point DFT where your capital N is equal to L plus P minus 1. That's all you have to do. So this is what we have seen. If you have length L and if you have another sequence of length P, the linear convolution of them would have a length L plus P minus 1. So what is it that you are going to do now is use an endpoint DFT where your n is equal to L plus P minus 1. So you make the remaining elements of that to be 0. So when you do that, the second copy would be placed at L plus P minus 1, and of course on the other side minus of L plus P minus 1, and then you simply take one period of it. That's exactly would be equivalent to the linear convolution. If you are taking just one period of it, okay, that is exactly same as the original signal. Okay, so how do you do it in practice? Assume that you have x1 of n, x2 of length, so L minus L. Okay, so this point would be equal to L minus 1 because it started with 0. This is P minus 1, of course. Then you zero pad them, okay, to have a length of L plus P minus 1. Okay, you do the same thing there. Okay, then what you do, then you, after zero padding the both, okay, because when you are doing then what do you need to do? You do a you compute so then the linear convolution and circular convolution is same, and now you compute this circular convolution. Instead of doing that, you multiply them in the frequency domain and compute the inverse DFT of it and take one period of it. Okay, so this is one example, again a specific example, very important result again. Okay, this you have to be very clear here. Suppose instead of considering L plus P minus 1 DFT, here what is shown in this example is, suppose if I just consider, if I do an L point DFT where L assume again L, one of this length of the one length is greater than P. Okay, just for our convenience you consider that, and with this you could think of a smoothing kernel, for example. This is your finite length sequence. Okay, what would happen if you are simply computing an L point DFT instead of your n point DFT where your n is not L plus P minus 1 but simply L? So you could see then, okay, the expressions we have seen there is that now x of n copies of that is placed at multiples of L. So multiples of n here, that is case of L. Okay, so that means actually so it is placed at L here, minus L here, for example. The length could be L plus, maximum length could be L plus P minus 1, right? So what would happen here? 0 to, so P minus 1 values could have an overlap here, and then you notice there x of n is the summation of all these sequences, right? So what's the consequence of it? The consequence of it is, on this side, p minus 1 values are getting corrupted, right? And you could in fact say what would be that value also. So if you recollect, the way we have written x tilde of n is equal to r varying from minus infinity to plus infinity x of n minus some r n. Okay, so what's the impact of it is that here p minus 1, length is l plus p minus 1, you considered only l, so the rest p minus 1, this is the time domain aliasing we discussed in earlier videos. So p minus 1 values are corrupted here, and of course the rest of the values are correct, so that would be exactly equivalent to x of n. Okay, these p minus 1 are corrupted, so how many are correct? So out of n, p minus 1 are corrupted, so correct values would be n minus p plus 1 values are correct values. So uncorrupted are n equal to l, so this is equal to l minus p plus 1 values are correct. And of course the this is within, what we are saying is within the value of n, but of course if you, there are other values here also on this side, but within the whatever result you are getting, p minus 1 values are corrected there. Okay, so that's all for this. Okay, so the take home message here, let me come back to the visual mode. Okay, click here, go to the read mode, come back to this, and then put in this. Okay, so that's all for the linear convolution using DFTs. Let me quickly summarize what we have done and why we have done so. First thing is, why you want to do linear convolution in linear convolution using DFT. That would reduce the computational complexity. Why would it reduce? Well, DFT computation, we have very fast algorithms which we would see in the upcoming lectures, and then the other multiplication is only of order of the length of the sequence, so that's all. So if you do it in the DFT and get a linear convolution using circular convolutions, then the linear convolution is computationally more computationally efficient. Okay, then all the throughout the lecture, all that we try to address is, when is that linear convolution and circular convolution are equivalent? Because we are going to circular convolution, we want it to be equal to the linear convolution. The answer is that if one of your sequence, that there are two sequences that you want to linearly convolve, let L and P be the lengths of those sequences. If the length of your n-point DFT, if your n is at least equal to L plus P minus 1 or any value greater than that, then your circular convolution is equivalent to linear convolution. That's all. Okay, with this we are done with this video lecture, and maybe we will have one more, just the last video lecture on DFS and DFT. With that we will move on to FFT. Okay, thanks for watching, and see you in the next video lecture. Okay, take care, bye.